Okay, so let me just revise, okay, what I said before last time, and then you can ask any questions you have. Okay. Okay. So we are now in the realm of auction design, and while we are talking about auction design, what we are also talking about is this whole subject of mechanism design, okay, where we are trying to design games. These are artificially fabricated games, but they are games nevertheless, because you have participants and there are a lot of variables of which we are not, I mean there are a lot of unknowns in the environment, right. We briefly talked about this at the very beginning. If all the aspects of the problem are pre-specified, you can look at a table or a graph and so on, you can just directly do algorithm design, right, you can optimize. But the point is, when we talk about games, when there are entities, agents, people, machines, other sort of algorithms whose decision, how they respond to a certain situation is not completely predetermined. We might have some information, we do not know exactly, and their behavior sort of determines our outcome. So, in that realm, designing games, designing situations where an outcome is a desirable outcome is attained is the realm of mechanism design. Okay. Mechanisms are these rules by which people interact, and the property of the mechanism is to show that, I mean, we desire to show that this particular mechanism gives good outcomes. Okay. So, as far as auction is concerned, these are the requirements that we want. So, auction is basically, it could be one item, bunch of item, whatever number of items that are out, like there is a buyer and seller this thing. Some people are buying and some people are selling their items. So, they are bidding, and we are talking about seal bid auction throughout. Even I do not mention it again and again, simply it becomes too verbose, but that is what we are talking about. We will briefly look at other kinds of mechanism, but now for the purpose of this seal bid mechanism. So, all that people are sort of holding on to is their valuation of the items that are on the auction block. Okay. So, that is the unknown variable. Based on that they basically they submit some bids, and they do it in, we call it sealed envelope setting. Basically simultaneously everybody submits their bid, the auctioneer opens up the envelope, and in certain situations the auction participants then understand what everybody's bid was, but that is not necessary. I mean, one way or another we do not really care. What happens is their bids get revealed to the auction, the person who is conducting this simultaneously. Okay. All right. So, that is the thing. Now, the auction designer's job is to decide on an allocation mechanism, who gets the item, and if there are multiple items, who gets how much, and so on, right, and at what price. So, mechanisms can be much more general than auctions. Auctions are this mechanism that work for this buying and selling of people. Okay. It is like a two-sided market where you have this. Okay. So, bidders, agents, these are the same things. Allocation rule and so on is the how you assign the items, and payment is like how do you extract a payment. And last time we saw that Vickrey auction or the second price auction has a very nice property that it incentivizes truthful bidding. Okay. So, and we call that property dominant strategy incentive compatible. So, and I said that, so we have seen earlier that all games need not have a dominant strategy. Having a dominant strategy is a wonderful thing from a designer's perspective, because you sort of have the belief that agents will figure out that they have a dominant strategy, and because they do not know what others are doing, they are likely to play their dominant strategy. That is the benefit of dominant. It becomes understanding, analyzing the game much easier, both from the participants' perspective as well as the designers. Okay. And here the type of dominant strategy we are kind of looking at is this sort of truth, say like truthfully bid your valuation. Okay. All right. So, that is what, so truthful bidding ensures maximum utility for all. So, utility is this object, that what is your true valuation which is unknown, and the price at which you obtain the item. So, this could be something, this, okay, this is defined as the utility when you get the item. It could otherwise be 0, okay, if you do not get the item. That is an easy thing to institute, that if you do not get the item, do not penalize people for participating. Okay. let us say xi is not 0, okay. Otherwise, okay. Individually rational is this condition that when you participate, your utility is not going to be negative, okay. So, it is either 0, this type of utility function automatically caps. Now, you also assume, okay. So, at this point, if this is the way the utility function is defined, right, unless this person pays more, rather bids more than his valuation is, he is not likely to pay more. Suppose somebody in that second price auction, right, you bid way more than your true valuation, then it might be that your second price, the person who is winning, the price you end up paying is also much higher than what, than your actual true valuation. In that case, you create negative utility for yourself. But we sort of see that a rational person should not do that, because they see that the second price auction is really good. If I bid truthfully, either I do not get the item, then that is fine, my bid was not high enough, or if I do get the item, I always have positive utility, because I am not actually paying my bid, I am paying the second highest bid, which is something less than mine, right. Okay. So, all that. Welfare maximization is the thing that I said at the very end, like up until then 1 and 2 is from the designer's perspective, these are desirable to analyze what would be the behavior of the agents participating, as well as people who are participating in the auction. If the marketplace is so complicated, just buying and selling it's very hard for people to participate. That oftentimes shrinks the market, you know. So, having simple rules that everybody understands is helpful. So, this is why. This welfare maximization is a objective driven criteria. So, some auctions, as I said, could be for the purpose of maximizing revenue for the sellers. Art auctions, I am selling an art which I have procured at a very high price, or maybe in my family, and I want to extract the highest price possible from the market. That is also the reason I am actually having the auction, and so on and so forth. But when there are many situations where, let us say, we will see examples like natural resources for a country, which when they get auctioned and so on, government wants to, it is this maximizing revenue is not the primary criteria, there are other things. There this welfare maximization comes into play. So, what this is saying is you want to maximize this quantity. VI is the true valuation of the agents. Okay, let us just write from now on, VI always means this, okay, private this valuation for I. Xi is how much of the stuff the agent I got, if at all. Okay. So, Xi is a real valued function, it is a non-negative valued function, Xi. Okay. So, I will say what that x bar is, but as of now this Xi here basically captures how much of the items did agent I get. Okay. And Vi in that perspective would be the valuation of the agent I per unit of stuff. Okay. So, it is like suppose this is a fruit market. So, they have a valuation per fruit or per kg. So, if they take 5 kg versus 10 kg, obviously the amount of money you get is different and so on and so forth, but this is what we try to capture. Okay.
Just one question, when we talk about Xis, are there like integral
Okay, I am going to make those as of now. Yes, that is what I am trying to say. I am saying unit of stuff. So, if the stuff is something that you can't just make, it is like not a cake, but a piece. It is like you are counting the number of items, but we do not necessarily restrict ourselves. The framework that we will discuss is very general. You will see how many things we can. So, Xi can take fractional values depending on what thing we are trying to model, what auction we are trying to. Talking about art and mangoes and all discrete, I mean you are counting numbers of stuff, right. So, in that, but there can be other examples. Okay. So, this is the thing that we are trying to maximize. See, it is not talking about how much payment the agent has extracted, anything else. It is just saying we are trying to maximize the total value, like the people, somehow people who value the stuff, right, higher VI value people should sort of be given more of Xi, correct. So, that is the general idea here, okay. That is why we call it welfare maximization. Some books may call it surplus maximization, but that is the thing. And computational efficiency, this is where computer science and algorithmic game theory comes into play. All this is in the realm of classical game theory and auction design. This is where our stuff comes into play, okay. All right. So, what is, so let us try to capture what an allocation actually means, okay. So, with respect to any auction, we will talk about a feasible set, which is basically some positive real valued vector, okay. What, so this is n, okay. So, let us say x1, xn. Xi, I should say, allocation with respect to bid. So, the bids that people submit is also seen as a vector, okay. N is number of agents, okay. So, first agent bids B1, second agent bids B2 and so on. In this case, take the, imagine it as if everybody is bidding per unit of stuff, okay. So, this itself gives a n length vector B. With respect to that, we are going to allocate items, okay. Now, the feasible set is a vector like this. Now, okay, some real valued vector, it is capturing how much let us say how many units of stuff. I guess, okay. And so, and price vector is again say okay. So, strictly speaking, this allocation, while we represent it as a vector, it is really also a function, okay, based on how much people bid decides how much of stuff they get, okay. So, this is saying, so tell me why do you think this is correct to actually predicate all this allocation and the price thing based, why do we see this as something of a vector, as something of a function on the bid vector?
We want to capture like whoever bids more probably has more allocation.
Well, okay, but that is not necessarily written in stone, right? Just because you bid more, you should get more. What we are trying to essentially capture is the thing that how much stuff I get depends on how much others are bidding. Whether bidding more gets me more stuff, that is a secondary matter, but it is a game, right, ultimately. It is not like n people are independently buying n things, which would be a normal shop such of situation. N of us show up and individually we buy things, and that basically the it is not an auction where the seller basically sells us all of us at whatever some fixed price and so on, right. Here we are competing for some objects. So, how we bid sort of decides how each of us, how much stuff each of us gets, and because the pricing is naturally should be defined on how much things we are going to get, right. So, it also becomes a function of B hat. It also actually depends on x, but x itself is a function of B, right. So, the price should be a function of the bids. Okay. So, all the additional property that bidding more should only get me more, at least should not get me less stuff and so on and so forth, maybe more price and all those things, right. So, those are secondary properties we add, but at least we agree that how much we get, each of us gets, depends on how much everybody is bidding. Okay, so that's where this is. Think of that utility function thing that we had, right? It depends. This it is defined over the actions of all the everybody. So here the action is the bid, because that's the only thing people have to do. No, how much you bid is your action.
That makes sense.
Yeah, you were saying something.
N is the number of players.
Yes, number of agent bidders and so on. Yeah. Okay. Yeah. For
And thinking of the bids as actions makes a lot of sense.
yes, so that's why it's a game. Whenever we talk about this, try to see who is the agent. Agent are obviously the bidders here. What is their action here? Bids. That's it. That's the rule. Just present your bid, and then the outcome of the game is who gets what, and also at what price. These are two things that are coupled, right? So this is the thing. Okay. So now let's look at some special cases of game, special cases of auctions. Okay. So single item auction. So there, this vector, there's only one item on say. This feasible set, this thing becomes a 0 1 vector such that, okay, I'm going to use this definition of Hamming weight. It means that how many coordinates are 1, okay. So yeah, so here the Hamming weight is at most 1. Why at most 1? Well, because maybe the item goes unsold or unallocated. So this is the thing, right? So single item auction, exactly one person gets it, and it's a 0 1 this thing. You're not having a sort of a dividing thing. K item auction similarly would be, again, these are indivisible items. In this case, I am implicitly, so Ham weight is at most k and so on, correct. Okay, actually here when I write the Hamming weight like this, it would be equivalent, when I say it like this, it would be equivalent to say summation of xi is at most k. Okay. Why I use Hamming weight is because sometimes when you are allowing fractional amount of items and so on, they all add up to at most k, but the Hamming weight could be much less, meaning there are very much fewer people or nobody is getting a single one whole item. So because I am talking about Hamming weight here, now I am talking about k items like discrete items, so I am writing it. But for this purpose, these two are the same thing, because the index, because the values are over 0 1.
Could you explain what's Hamming weight?
Hamming weight is just that how many indices have 1 in them. Okay, that way.
Maybe the generalization when will sigma xi at most k?
So if I allow fractional values, so this is actually defined over real numbers, right? Positive reals. So if I give fraction, it could be like k is equal to 2, 4 people, half, 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 add up to 2. But Hamming weight is 0, that sort of thing. But here it won't happen because I have said it's 0 and 1. Okay. So these are rather simplistic, simple auction. Now let me tell you about an auction that really got the internet industry booming. I mean, this was at the heart of the internet boom at the very beginning. Internet marketplace, in particular, the buying on selling of ads that we see whenever we open a browser and search something. So that particular, it's called sponsored search auction. Okay, I'll tell you why sponsored. The point is, when you're searching for keywords, that's when this auction happens. Some companies have already bid on certain keywords well ahead of time. Your browser has only so much space to show ads. If they fill the entire browser with ads, nobody is going to use that search engine. So they kind of have to do a good amount of cost benefit analysis. One of the defining principles that Google had at the very beginning, and I suppose it still is holding on to it, was that our search will remain, the quality of our search will remain unbiased. How we but obviously it's a very expensive thing to have this many employees just to keep on the search alive, right? So somebody they have to generate revenue. So the idea was to monetize the search in a way that while they are earning money, it kind of remains independent of the quality of search that we get. So this is why they very clearly write sponsored ads. That's the part where they are allocating to companies or merchants who have bid for this particular term. Okay. Now, suppose, so sponsored search auction is this situation where you have k slots in which to show ads. You have n agents here, as always, bidders who have showed interest on a particular search word. So, the item here on cell is a keyword. Okay. Number of agents remains the same. So, the goal here, and these slots are not all the same, let us say. Some slots are more impactful than the other, meaning if you show your ad there, people are more likely to notice it and pay attention and maybe buy your item. The way this particular auction differs from auctions such as like this advertising, let us say. How is this advertising different from the traditional kind of advertising? Firstly, there is this auction format that people are basically bidding for their sort of what should I say, their not ownership, just at that moment in time when this search keyword is this thing, to have their ads displayed. At a different time, some other set of ads you might see. Okay. So, each time you search, a new auction takes place. That is one thing. It is different from those, so this is advertising, of course, right, because you are showing ads for some companies and so on. It is different from those highway hoarding type of ad where you sort of go by in the cars and you see ad, you know, like a hoarding there with an ad on it, or newspaper ads and so on. There, the moment you buy, it is like you are purchasing a real estate, renting a real estate. You are purchasing that ad and you are giving money, whatever the rate is, and that is it, and they show the ad. Here, this, how they display the ad has sort of Yahoo, Google, they sort of take share the risk of with the advertiser in this very sort of meaningful way. There is a belief that certain ad slots have higher value because people are more likely to click. Now, just because they are showing your ad does not mean they will actually get money for it. Only money is transferred if somebody clicks on it. So, the click through rate, the probability that a slot J will get clicked. Okay. It is very simplistic, but this thing. How they decide this, how they know this is again a bandit problem. Okay. How they decide this from the market, it's a whole other subject, but suppose we know this, that the probability that if my ad gets displayed on slot J, this is the probability that it will get clicked. If it gets clicked, the search engine will get money, not otherwise. So, what these companies are doing, they are basically saying that you can trust our quality of how we are displaying your ad, because that will basically directly impact our revenue. If people do not click, we do not get any revenue. That does not happen in other sort of traditional form of advertising. Here, there is also an inherently a matching question. Over there, the moment you have an auction, there is a natural matching. These are the items, these are the agents. How do I, this allocation is basically a type of matching. Allocation rule. How much item you give to whom, that is a matching. Now, matching, not the graph theory is classical matching of one-to-one relationship. We are talking about a more generalized matching, where one person, so word matching in terms of most like assignment. Okay. So, all these things come to bear in this question, but this part of how to assign, so many people are bidding, they know there are only k slots, based on their bids, the ads get displayed. Okay. And okay, so this is the thing. So, because of this difference, alpha j being different for the different j's, companies would like to want to be on a slot which has higher probability of being clicked, because if you do not even click, it means you have no interest in that company. Like you're not going to buy or rent their service, nothing if you don't even click on their link, right? So that's the idea. Okay, so this is the situation. Okay, so now here the goal is what? To assign so there are exactly case there are case slots and so on. Again, sorry. Okay. Okay. So xi is the this is the allocation. Who gets what? Okay. This is the alpha j value if you are assigning agent I or this to slot j. Okay. 0 otherwise. Okay. So xi, so x, this thing, what is it called? Sorry, this is basically a fraction. This is a probability, right? So it's a vector defined on this. Okay. This allocation vector. It's a 0 1. It's a defined because there's a probability, right? I'm assigning alpha j. Now, more interestingly, now if I see how many of the coordinates are non-zero, that has to be at most k, because there are only k slots. Okay. So if I okay, so I did not okay, let's just use this. I don't want to introduce any more notations here. Okay. So this is like this basically means this is the number of coordinates that are strictly more than 0 is less than equal to k. So see, because I am assigning this, I can't really count Hamming weight, right? All I am trying to count is the number of indices for which xi is non-zero. Yeah, basically you got some assignment. No, Hamming weight is strictly defined to be one where the value is 1, but yes, there could be a Hamming, there is a this thing, but I already said Hamming weight is like counting number of ones. So if I change it to counting non-zeros, then I should adjust this to saying n minus k and so on and so forth. So because over here I was just counting the number of people who got stuff, and there are only k things, so this way. Okay, so number of xi, so that this is so this is where this captures all the constraints, right? Let's write introduction. Okay, all right. So the auction here is basically who gets which slot, which is essentially who gets what click-through rate. Okay, all right. I mean, there are a little more subtleties here. I'll just mention briefly. Notice, just because these slots are not like static, just because you assign some unknown company at the very first slot, let's say that's the most impactful slot, does not mean people will click that. I may have some companies in my mind that I'm actually looking for when I'm searching for that object, and even if they are placed down below, I am likely to sort of click on this and so on, right? So this click-through rate is not necessarily just a function of the position. It also matters who is occupying those positions, but that makes the problem even more general and so on. So as of now, we agree that certain slots have more visibility and therefore have a higher potential for the advertiser. Okay, all right. So we will use this as our test sort of case on which we will test our theory. Okay, so I think I have. So now, do you have any questions from last week? Last class actually, before we proceed towards a more sort of a formal explanation. I want to
then say that the kind of dominant strategy will be unbiased.
say that again.
The search engine or the mechanism we want to come up with is unbiased to all the agents.
So what do you mean?
Like cosmos.
Unbiased as in? Yes, it will only depend on their bids and how we assign, okay. Alright, so I am going to suggest a greedy algorithm. To the highest bidder, assign the top slot. Second highest bidder, assign the second slot, okay. Yeah, ith bidder. Let's say, okay, we can just assume some notationally that alpha 1 is of the highest impact versus this, yeah, okay. So it means the first highest bidder gets the first slot, second slot and so on, okay, yeah. So this is the allocation rule, correct. Now the question is, what should I charge them? What should I price them? Like how should I, like what would be the value of this is what I am this thing, okay.
I want my auction to be as ideal as possible.
Yes, exactly. I want it to be, and we will see how, like how close we can get to this, to satisfying all these criteria and so on, okay. And we will also see what they actually do in real life and if that is ideal and so on, okay. All right. Now I just want to say this framework, this whole thing is what we call a single parameter environment or single setting. The term single comes into play because the only unknown is this Vi. That is the one thing that is unspecified. For each bidder, that is the only thing that we do not know. There can be other situations where basically what we do not know, like in a very complicated combinatorial type scenarios, where people have valuation not just on singular items, but bundle of items. Some items make no sense to them without the existence of another item in the bundle. Then their allocation, their valuation basically is not item per item, or in this case like slots for slot, like this is the slots are the items here, but over subsets of items, okay. So that is a much more complex scenario and we will see that later, but over here we are talking about this single. So I am giving you as much technical and as well as this thing so that we remain precise, okay. Okay. So now it is remarkable how many people won Nobel Prize, all the people that we I think talk about. So Vickery, just that simple auction laid the framework for basically auction theory, like the rigorous study of auctions obviously have been happening for hundreds of years, but economists have studied it formally, I guess from the 1960s, and his work sort of stands out as a seminal work, okay. So Myerson is also a Nobel laureate, again economist, but this one I think he won it for cooperative games and so on, but okay. So Myerson's lemma, I will state the statement precisely and then we will talk about it, okay. Okay, right, I didn't say let me write little bit more. I am going to remove this, okay. Is this visible here? Let me write it here. We want to erase this, okay. So I wrote things fragmented way over there, but let me write it here itself. This is the thing. So this was the way the utility was defined when we were sort of giving out items. If I were to generalize this for the possibility when you even can get pieces of items, okay? And valuation is defined as private valuation, valuation for agent I for unit of stuff, right. So, the utility also gets defined in that way, sort of utility of agent I, the bids that have been submitted is equal to same thing. See, over here it is the true valuation minus the price I paid, here it is VI times XI, the utility, the amount of stuff I get, again this is a function of this thing, minus the price I paid, okay. This is how utility is defined, because we discussed why, right. That comes from economics, that this is the idea, that how much value I got from this transaction. Okay. So, now can you tell me some, is there, I am going to assume, I should write the single value, single parameter environment somewhere. Okay. Each of the PIs is greater than or equal to 0. This property is called positive transfer. Like there is a term for this, but what this basically means is that the auctioneer is not paying people money. Yes, okay. So that is the thing. Okay. So, you are not paying people money, the agents who are participating. So, what he is saying is like you are not injecting, like the money that is there is because of the money paid by the bidders to the winners to the sellers, and sellers are not transferring money and so on. Okay. So, this is the thing. Also, we will assume this thing, okay, falls within the range of, what do you think should be the upper bound? BI? BI or BI?
Yeah.
You are saying this? Why?
Like, I want it to be as close to ideal scenario as possible.
But this BI is not known to me. The only thing I know is BI. So, imagine a situation where your valuation is very high, but you are bidding BI. You should not be charged more than your bid. So, this is why, right, based on how much you are bidding, see based on how much you are bidding, you will basically, you bid BI for each unit of stuff, you ended up getting XI unit. So, your total money, basically the money you are willing to pay to the people, you are expressing, yes, expressing your intent of paying, how much money you are going to pay for this amount of stuff has to be BI times XIB, right. That is what you are telling the auction house, that this is amount of money I am willing to pay, even though your actual valuation might be much higher or lower, right. So, this is why this basically says there would be no money paid to the agents by the auction house, and no agent would be made to pay more than their bid value times the amount of things they are getting. Okay. Notice something, the actual utility of the agent sort of will always be an unknown. Unless I know VI, I actually cannot compute that. Then only the agent can know what is his actual true utility, right. So, you have to know VI to compute the utility value, right. The beautiful part about this thing, this guarantee is that even without knowing that private information, the design mechanics is the design of the auction is such that people have the sort of guarantee that as long as they are bidding truthfully, their utility will be maximized, This is why it's a non-trivial, it's sort of a even an interesting result. If if all the VIs were known and so on, then there might be a much simpler auction, right. This whole thing is happening without actually the precise knowledge of VI. Okay. All right. So, now I think we are there, we have all the at least the terminology needed to this. Okay. So, there is a notion of implementable, I am just going to define some terms here. Implementable rule. Okay. So, X is an implementable rule if there exists a pricing rule such that together they become DSIC. By the way, when I say DSIC, I mean DSIC and IR. Okay. I keep on saying DSIC because it's like two things, but what I mean in DSIC and IR. Okay. So, you can assume that DSIC for the purpose of this captures both, or else I will write it explicitly. Okay. So, ideal auction basically requires me to find such a rule and a payment policy such that it gets a DSIC thing, and it should be computationally fast and all those things. Okay. Now, notice, now let us come to this thing that Wipro was saying, this monotonicity of the rule. Okay. So, for an agent I, B minus I is, we know this notation, it is everybody's bids but I's bid. Okay. So, if I look at the allocation that I gets for an agent I, he bids Z something, this is a variable, but everybody else bids the same thing. This is a function. Okay. This is some value that has been held fixed, everybody else is bid being this is his value. When I see this allocation, how much he is getting as a function of this Z, this should be a non-decreasing function. So, meaning if Z is higher, you should at least get the same amount of, if I increase Z to Z plus delta, okay, the amount of stuff you get should be at least as much as what you were getting when you were bidding Z. Okay. So, this is, so it can be equal. So, this is why we say non-decreasing. It can remain same or it can increase, it will not go down. All right. So, notice something, there is nothing about DSIC that inherently tells me that it should be monotone, correct? All right. But we will see that there is a relationship between implementability and monotonicity, and that is an important thing, because see this definition of implementability is like there exists some pricing rule. What is that? I mean, price is after all some searching on the real line, right? It is some numbers, and then you have n people. So, it seems like a weirdly complicated search thing, right? Monotonicity on the way allocation tells us, well, this is saying that some x is implementable if you find a pricing rule. Who gives me the pricing rule? This tells me, well, we are talking about some specific class of rules, ones that are non-decreasing. Okay. All right. So, okay, everything here I am saying is in terms of the single parameter environment. Okay. So, I am not stating it saying, but that is sort of something to keep in mind. Now, Myerson's rule, it's this thing only holds for single parameter environment. So, I am just going to write this. Okay. Allocation rule, I am going to write AR. R is implementable X is monotone. if x is monotone. There exists a unique, so it's a, the function is uniquely defined, okay?
SP,
Huh?
SP.
Or single parameter environment. So in those definitions also, we say in a single parameter environment, an implementable rule means blah blah blah. In a single parameter environment, a monotone rule means this and this. See, because as I gave an example, when we are talking about when we have valuation over bundles of stuff, the size, like it becomes much more complicated. Like monotonicity may not be there. Like I might be interested in a very small bundle, have a very high valuation, and it is not as much for a large bigger. I mean, it's just a different thing because the items matter and so on. Okay, the subset matters. Okay, so I was going to say something. The unique pricing rule P such that this sealed bid auction such that bid auction is DSIC. Okay, all right, I'm just going to assume, okay, assume, I didn't write this, but if nobody bids, nobody gets anything. Okay, so if your bid is 0, okay, no matter what others are doing, you don't have to pay anything. Okay, all right. Okay, and this is like P is described by an explicit formula. This is the beauty of, and we will see what that formula is and so on. But let's just process this. An allocation rule X is implementable if and only if it is monotone. This Myerson's lemma, the statement. What we are saying is that in a single parameter environment, we have these three properties. Any implementable rule, meaning a rule that for which there exists a pricing policy that makes it DSIC, it is monotone. If a rule is monotone, it is implementable. For it to be implementable, obviously again we need a pricing policy which will make it DSIC. That pricing policy has a unique, it's uniquely specified, and the specification is constructive, like you can define it explicitly in terms of a formula. So that is what makes this remarkably sort of the word implementable is getting used many times, but it's like you can implement this entire mechanism, because all you have to do is, if this lemma is true, and we'll see why it is true, we'll see a proof. Yes, an monotone allocation rule, right, will have a precisely described pricing policy such that both of them together will give me a ideal auction.
I'm guessing it is important because unlike other reserves that just give existential stuff.
Yes.
Not
Yes, this being able to say that what that pricing policy looks like exactly tells me how I can construct, okay, not that there exists such a pricing policy, okay. This is what makes it like a so completely useful in a very sort of everyday sense of the term, okay. So now this is the part, this is, yeah, so I think, so I guess you all understand, having this monotonicity from going from implementability to a DSIC mechanism requires me to find some pricing policy. Now this relationship basically takes me via a much more easier to understand world, which is this monotone allocation. Like at least we understand how it should be. If somebody bids more, they can only get stuff. I mean, if they were not winning before, now they should get stuff. If they were winning something before, they can only get higher and so on, right? Okay. All right. So now let's see this. The proof is very interesting. I don't know if all aspects of this are established together by basically just analyzing what a DSIC type mechanism should be. Okay. And by the way, I am going to prove, just for the purpose of just understanding and this, in terms of the allocation rule, which have sort of they have like this sort of a jump prop. So initial, so let me write here, this is the X, this is the bid, okay, let us say this is Z, this is this. So initially, if your bid is too low, this is the bid and this is the allocation axis, same thing here. So if initially when your bid is too low, you basically don't get anything. There has to be a point where there is a jump where you basically get something. So if there is only one item, there is only, if you cross this value, think of it as like the highest bid submitted. If your bid is higher than that, like you just, this is like an open point, okay, and then you basically get this item when this. So this is why the allocation has jumped to from 0 to 1. This is basically that sponsored search situation where basically, okay, there are n agents, everybody is not going to get a slot assigned, but there are values associated, and if you sort of cross over, so that greedy allocation thing, see, these are, let us say k is equal to 3 here, 3 slots. This is for the first highest person, okay, he gets this, his assignment is highest, basically saying that he got the highest alpha 1. This guy's is alpha 2 and this is alpha 3, right. This is the greed, this sponsored search with respect to greedy, right. The person who bids the highest gets the first slot, that is this guy. The person who bids the second, so notice if you are bidding between what was the second highest bid and the first highest bid, your situation does not change, right. If the person who has won the second slot, he sees what is the difference between him and let us say the first bidder, he realizes that anything in between would not have changed my situation. I would have continued to get the same thing. I only could have gotten to the first highest bid if I cross over this. That is what these jump points basically indicate. All people who are all agents n minus k are basically in this realm. They are bidding lower than the kth guy, kth highest person. Therefore, their allocation remains 0. Okay.
Bidder has to make like kind of two choices only to go which of the extremes to go.
Which of the streams meaning?
Like suppose bidder for alpha 2 person.
Yes.
So he or she has only like it can either fall to alpha 3 or jump to alpha 1.
Okay. Yes. But he does not know it when he is bidding. But that is basically, we are analyzing, that is basically what the situation is. So for him to have, you can, that is a good intuition way to think. The reason this guy jumped from alpha 3 to alpha 2 is because he went across this point where alpha 2, where the assignment from alpha 3 to alpha 2, let us say. The person who got the alpha 2, the second slot, did so only because he surpassed the bid of the next lower guy who is the third person, correct. So this is why his allocation piece sort of starts to the right of it. This is the bid axis, right, and yes. So keep this picture in mind that you kind of have to navigate these jumps to change your allocation. You remain in this flat area, nothing changes, wherever, whatever you were doing this thing, this, okay, all right. So now these are the piecewise constants thing for, this is for one item, this is for k items, but these are the piecewise constant allocation rule. a similar, I mean it requires a little bit more calculus, like you can have more general allocation rule which are don't have this piece, they don't have this sort of a piecewise constant property, they are, let us say, differentiable the entire this too. So, they are basically smooth and so on, but the idea is same, instead of summation we will do integration, that is it. Okay. All right. So, how am I doing? Okay, half an hour, not bad. Okay. So, let us take a variable, we are going to talk about two variables, okay, positive. Okay. We are going to analyze two cases, this is an analysis. Okay. What is actually happening, we will analyze that from the DSIC perspective, what is actually must be happening, and from there we will derive some conclusion. So, when this is the case, consider the case when a person is overbidding. Okay. So, then over here the variable means what? You are bidding more than your true valuation. Y represent your true value, correct, and Z is your bid value. Okay. If this is the case, what does DSIC tell me should happen in terms of utility? Negative meaning. Okay. So, DSIC says that you will get maximum utility as long as you are bidding truly. So, it means that if you are not bidding truthfully, either you are overbidding or underbidding, your utility can only be less. That is what this says, and the way we compute utility is what we will use there. Okay. So, this is the true value. So, we will compute in terms of this y, what should be the expression here, xi b minus price. Okay. So, I am going to talk about each fix an agent. Okay. The same idea apply, this is like agent independent, fix agent, we are arguing for agent I.
Price, okay, price is the total
Yes.
for xi many items.
Yes, correct. All right. Okay. So, this should be at least as much as whatever the utility I derived by bidding this. Wait. Okay. Yeah, sorry. I am like sudden. Okay. I am using, this is the bid value. See, Z represents B, there is no B here. Okay. Let me see. Z is representing the bid value is greater than equal to
But B will be the entire
wait a minute.
that is
Yes, okay, right. So, this is let me just, okay, it is going to become very what I am trying to write here is the following, and I am going to write here once and then I am going to just basically I was writing this Z for this guy I and B minus I for everybody, okay, and similarly for price. So, let me just say here I am yeah, so yes, so wait, so I am going to write, let us say if I say like this is supposed to represent XIZ B minus I. This is actually what needs to happen because I need to feed it this thing. So, the bid everybody, that is why I fixed an agent, all the other people's bid remain the same. If this guy agent I is over, like he is the one whom we are analyzing, so that we are representing as this variable Z. Okay. So, this way. Okay, so wait. Okay. White times, yeah. Now I can minus, yeah. I should write smaller. Yes. Is this correct?
Z equals
Okay. Sorry. True bit is, okay, I shouldn't follow this thing. The notation there is a complete, it's different. Yes. Okay. Notice something. This is just application of this. This is my true bit by definition. Y is representing my true bit. Xi is the allocation given to this agent I, and B, there is a B minus I, that term. So, okay. So, price is based on this. This is truly the true value, true utility I will get, right. This is DSIC says for any agent, okay, I should say a DSIC implies this. The true valuation remains unchanged. This, however, my allocation will depend on what I am bidding. So, this is the utility due to bidding, correct, due to overbidding basically, but this is nevertheless this. Now, underbid is the situation where the exact opposite happens. Now, Z is representing true bid, true valuation. Y is the bidded, the thing that I am submitting the bid for, okay, because I am underbidding. Here also DSIC will say that the true bid value would have gotten you more utility. So, this should be Z XIZ minus PIZ greater than equal to this. Instead of Y here, I will have Z for the same reason, except these things change. Okay. So, Y and Z are variables, they can take on any value based on case 1 or case 2. These are the two things that can happen. Okay. So, 1 and 2, if I rearrange, what do you get? Just take the group the PI's together and so on and so forth. So, what do I get? So, I get PIZ minus PIY. This thing.
what does grouping of these two equations?
Yes. So, we know grouping of these two things mean that either the two cases, whatever happens, Y and Z behave this way. Y and Z are two way, one Y is sort of following Z. Either case 1 happens or case 2 happens. The value of the way PY and PZ behave, we basically are going to get an inequality which captures like this thing that the variation, like they vary over a certain range. So, let me just write this and then we will see what how to infer this. So, I do not know PIZ minus PIY. So, here there should be common term is Y. XIZ Z, same thing, XIZ. Check once please. I think I should, but it's a possibility. So, this pi z comes here, z times x I y goes here.
First inequality looks okay.
This the second one is wrong. It's fine, right? So, pi y, yeah, okay, okay. So, I have basically moved this, pi z goes there and so on, okay, all right. So, let us now see this, okay. What we have is this, the way, and we still have this thing, y is trailing z. The way the price changes from y to z, it's this quantity, the variation in price, but it's sort of sandwich, how far it can move basically is decided by this thing. This is basically saying how much more of stuff you can get if you move your bid from y to z. The same, this is basically the same quantity, okay. Let us call it alpha. And this is the y value and this is the z value. This is that, okay. Now, notice here something. Let us now analyze this in terms of if x was a function like this, piecewise constant. X, allocation. Let us say case 1. Again, y and z are two variables. Let me take another chalk. Maybe it. Okay. Let us say z, we are in these flat areas, there is no breakaway points, okay. Z is some point here or here somewhere or like this, okay. Yeah, I should say it like this or this, okay. These flat areas, not these jump points. If y is somewhere behind and it's just tending towards z, it's approaching z, nothing changes, the allocation does not change, it remains the same. Over here, allocation was 1 before, if z is somewhere here and y is somewhere here, see, from here to here the allocation does not change. Similarly, here also, if they are in these flat areas, the allocation does not change, correct? Okay. There is not, I sometimes call it jump. What did I just now say? Break or jump point? Did I use a word? Okay. Okay. I said jump, right? Okay, maybe I have, I don't know why I am thinking break curve point, the jump point, okay. Then y moving towards z does not change, so it is in limit, okay. This is where it is actually a calculus argument which I am trying to discretize, and a lot of people use it just to explain the intuition behind it. So, y is tending towards z in limit does not change x. Correct. So, basically what that means is this x I z minus x I y is basically 0.
Or eventually 0.
Yes, meaning as y tends to, it tends to 0, let us say, okay. Okay. Nothing change, okay. So, okay, the way I said why I am saying it is 0 is because I am saying I am already in this region. So, that whatever you are going to get an allocation with y, the same thing remains. So, this is why I should really just say 0, okay. All right. So, case 2, why I changed, let us continue with this. Yeah, now tell me z is a breakaway point, is a jump point. Now, what happens? So, I might accidentally kick. This is the z, this basically this point when projected down, this is where z is. Now tell me what happens. Y is again moving towards Z, which is a break point. Now what will happen? Z is exactly this point, Y is somewhere here, but it has not reached. Now when Y tries to move towards Z, its allocation will jump. Yes, if it was 0 before, it will become 1. Sorry?
Moves to the next level.
Yes, over here it was like, let's say Y, if this is the Z point, break point, right? Yeah. So, and Y is somewhere here in the vicinity, right? If it comes close to this, the moment it reaches Z, the allocation jumps to the next level. This is the difference between when we breakpoint behavior versus when you are in the flat areas. Okay. Changes allocation. How much does it change?
In that case, one, but otherwise it's alpha.
Yes. So, basically what we say is the height. Really depends on what this is capturing. Over here it was capturing one item 0 1, over here we are capturing this, right. So, it is the jump, changes allocation. So, how much does it change? Jump from xy to xz, right. So, that basically means the difference xy xiy minus xiz. Okay, I should use a, okay, see, okay, okay. Now, if this is the behavior, can I say something about x? Can I say if this is the case, I missed an important point which I now realize I should have said this, but okay. Now that we are there, let us see. So, just examining this, can we say something about the allocation of, can we devise some property about the allocation? Like what is xi? Can it be what, because this inequality has to hold, right. One thing we are seeing is if you are at a jump point or not at a jump point, the allocation value changes, right. So, if we are at a place where alpha y is less than z, if, yeah, is it possible that xiz minus xiy is actually a negative quantity, meaning alpha is a negative quantity? No. I am saying using this inequality, alpha is just this difference, whatever we are calling the jump. Okay, for the moment, let us call jump as, quantify it as whatever the difference. Okay, all right. So, as such, I do not know whether I just drew this in a way. This actually is capturing the greedy allocation, but the x function could be very different. Yeah, I mean, why should it have to be monotone? Maybe it changes in a weird sort of way, right? All we have assumed formally is that x is a piecewise allocation, piecewise monotone, piecewise constant. I have not said anything about whether it's monotonicity is something that we have to prove as part of this lemma. So, but all we used here is that DSIC says all of these things. This is also true and this is also true. Whether you overbid or underbid, both of them are true. So, as variable y and z, they exhibit this property. Now, tell me what happens if alpha is actually negative.
Negative quantity multiplied by larger number is greater than negative quantity multiplied by smaller number.
Is it possible? Correct. Given that z is greater than equal strictly more than y, alpha cannot be negative, correct. Therefore, what does it mean? So, yeah, okay. So, star, so we observe that since Z is greater than Y, it implies, star implies basically, star is this inequality, that alpha should be greater than 0, which means x, y, z is greater than, that is greater than equal to 0, right? Yeah. This is alpha x I, yeah, z is at. So, this is what I get the monotonicity, that DSI, if you have a DSIC mechanism, you already have a implementable rule, that is a definition of DSIC implementable, right. That rule has to be a monotone, correct? Okay. Okay. Now, you see, because of this monotonicity thing, now we know this jump has to be positive, okay, all right. So, this is the jump, okay. So, now from here I am going to infer a pricing rule that then we are going to prove is the actually correct one. So, all this was telling me something about the pricing function using the property of DS. So, using the property of DSIC, we inferred that x has to be monotone, the allocation rule has to be monotone. So, we prove this for each I, agent I. So, the monotonicity property was like for all I, if this function is non-decreasing, then I know it is a monotonic this. So, this is basically what this means is, it is non-decreasing for each agent. Therefore, the allocation rule x is monotone. Now, it is monotone. From here, there is no space left, okay. From here, can I infer what the pricing rule should be? I will call this Myerson pricing, okay. See, y and z again, we are talking about two variables that are basically traveling over the real line. Based on whether what is their position vis-a-vis the break jump points, we can infer some properties. In order for, and because of the monotonicity rule, we can basically see that in this sort of a, whenever x is this piecewise constant thing, also monotone. Now, we have piecewise constant monotone rule. The idea is for an agent to get an allocation of this kind, this much allocation, right. This is because this, the height of this is what tells me, right, the allocation, this thing, because that is measuring across along this axis. This agent has to have covered all these jump points. These jump points are basically where a phase transition sort of happens. You get to a so over, imagine for him to reach this point where he gets this allocated. If he were, if his bid was like a scale that was going up, when he was initially 0, up until this point he got nothing. Then the moment his value navigated this jump point, he would have been assigned the lowest valuable slot. Then once he went across this, the second lowest spot, all the way when he arrives here, he basically has to cross this jump to get to this. This is what, even though we are, this diagram is for that sponsored search, but this is basically a general principle that for a person to get this much of allocation, yes, he has to cross these jump points. So, his bids have to be greater than all this, yes. And if I look, and the most interesting part here is, if I look at his allocation this much, I can basically look at, break this, decompose it into these smaller height jumps, this jump in allocation. This entire thing is made of what? This much height plus this much, correct?
All we need to do is define the pricing at jump points.
Yes. And the allocation, pricing at jump points tells me the allocation at jump points, right. And so, the entire allocation is split into jumps in allocation at those jump points.
Previous jump, so I just break it into the components.
I basically decide where the price should be, yes, and that will determine the jump, and the quantity of jump will basically say will decompose this entire thing, right. Okay. So, let us write this down then. For price, Myerson's price Pi is equal to, so here it's, oh there is a chalk here also, okay, J equal to, okay. Jump okay, let's write it this way only, jump at in x I at zj, okay, where is zj, z1, z2, z k, let us say, are the jump points. Okay. So Z1 basically there, because we are talking about that k slot, k objects and so on. So, that is why there are k jump points. Initially everything is flat 0 and then you have these k places where something different happens. So, that is why I have written it this way. Now, if the agent, so L here is, this is the thing, I do not know how to, L is basically the number of jump points to the left of this guy. This is what this L is. Okay, L is like number of zi's, yeah, okay. Yeah, so if I write zi to left of this guy's true bid, which is, let us say, should I say y again, of sorry, this is okay, tell me. Yeah,
function has to be proportional to the valuation and quantity.
Valuation and quantity. Quantity is this allocation. Yes. So, but why do you say it has to be proportional? No, why do you say it should be proportional? And what way should it be proportional? So, when we said, so in this Ponzi greedy, all I said is the highest bidder gets the highest lot. I did not say how you charge this person, correct. This is a pricing rule that we basically devise looking at what a piecewise constant allocation this is doing. If we use a monotone rule, meaning more you bid, you should get higher this thing. If that is the case, it must mean that if you are at the tth slot, you must have beaten k minus t people. So, those the bids that these people submitted, those k minus t people who are at a lower level than you, their break point you have had to cover. That is all I am basically saying that over there. And the reason you are here is basically sum of this quantity, this height plus this height plus this. Okay. That is what I am trying to say using this thing. This is the bid, or I mean you think about why and what, how did we get this quantity, right? The bid minus the jump in allocation. Okay. So, this is an inferred formula that something like, it should look something like this. It is a thought experiment. Why this works still needs to be seen. So, we did use the definition of DSIC and inferred some property, that star and the monotonicity. And using the fact that that sandwich thing, it seems like this is one possible pricing rule. At least this rule satisfies that kind of behavior. Okay? All right. So, okay. How much time? Okay, we have. Okay. So, now the proof from here, maybe I do not rush through. I wanted to say a lot of things, but okay. Okay. So, let me just say briefly. Okay, so maybe we come back to. So next time we will just see the proof of. We started a little late. Is it clear so far? Then I can try to give a proof of what is happening, why this is the correct pricing rule. Why this is this thing that we are promising.
In the monotone setting, this makes sense. Monotonically, piecewise constant monotone setting makes sense.
Okay, so all we did. Okay, so if it was not piecewise constant, but it was something that was x is differentiable and all these nice properties and so on and so forth, what do you think will change? That inequality will change to what? Why? So the difference remains the same. The point is what kind of function xi is, this quantity, it remains the same because this is the definition of what a utility. DSIC promises that the utility should be maximum if you bid truthfully. So, and what is the definition of utility? It is a quantity that looks like this, your true bid times the amount of stuff you get minus the price you pay. So, the only thing in this this expression that changes is that instead of xi being piecewise constant, is just a more general function. Okay? It is a differentiable function, let us say. In that case, but the meaning of it does not change, right, regardless of what xi is. So, the sandwiching property also remains the same. What then changes is this sort of a thing. When we are at a jump, this would be a rate of change of the function xi. Yeah, that's no. The rate at which this changes. So, you can have a function that sharply rises like this. Why would this not be 0? But it is not a breakaway. So, it is, suppose it is something like this where the rate of change is 0. These points, this sort of flat regions are demonstrating those cases where the curve does not have, like, the rate of change is 0. So, if the rate of change is 0, it means your allocation is, rate of change of this allocation function is 0. So, it means that the allocation is remaining the same. So, this still holds. Okay. So, the flat region for a more general allocation function, the flat region basically demonstrate there are representing regions where the allocation function is basically flat parallel to this thing axis. That means what? The rate of change is 0. So, if the rate xi minus this quantity basically captures what is the rate of change of the allocation function in these 2 points z and y. So, that is why I said when in the limit when y is approaching z, this quantity will remain 0 because the function itself is not changing. Okay? Yes. By the way, this part, okay, this portion, if I just restrict myself here, this portion is this is fine, right? Nothing changes. The point is what is happening here. Here there was a sharp change, like it went from 0 to 1, 0 to alpha 3 and then from alpha 3 to alpha 2. This, if it remains a gradual curve like this, instead this jump would be basically this jump that I wrote, exercise this would be captured in terms of the rate of change of the function in the vicinity of the breakpoint z. Okay,
Summation will be
integration. That's it. And we will see if we have like maybe 5 more minutes or 10 more minutes, whatever, that let me not erase this, okay? Okay, so I don't really. Okay, so let me draw some figure. Let's see. A little bit. I want to draw the exact same picture 3 times and like 9 times maybe. Okay, so this is when true value is equal to bid. This is true bid less than true value is less than bid. Okay, this is the overbidding part. True value okay, I'll just draw this line, you'll know. Okay, let me just draw that. This is supposed to be the maybe this is where slides do help. It's supposed to be the exact same picture. Okay, let's say this is the VI value. Again, this is the bid axis. This is the allocation axis. So somewhere it should be here. So bid is somewhere here. Okay, it's bigger than this, and let's say bid is BI. Is the is this very different? It looks different. It looks more flat than the other one. Okay. So here I'm going to map this quantity VIXI. Okay, this quantity here, also this. Then we will look at the price and then the utility. So what is this? This is utility, you will recall, is this quantity, right? VI times XIB minus PIB, right? So this is what sometimes it's called the surplus. So on. So this is what this is. Okay. So how do I capture this in this picture? Tell me what is the area? Let's shade this region. So VI is actually equal to this. So this is the XIB point, correct? by this. What am I multiplying? This is the, so this horizontal portion is the Vi part and this is the Xi. So, this region, correct. Here what is this? See, again this is the, again this axis. Xib is what? What is Xib? This person, his bid is this, right? So, Vi, this is this, yeah. So, I basically, so I am going to get this rectangle which is in case between this, yeah. Height of the rectangle is this, correct? So, Vi times Xib is this value, correct? What is happening here? Let me just draw this. So, the bottom of the rectangle always remains this Vi value, base of the rectangle I should say. And allocation, what is it? It is decided by, yes, this part, correct? So, I am basically, yeah, right? Okay, this is not needed actually. Okay, now similarly, okay, let's just finish, take 5 more minutes and just finish this, okay? Difficulty is reproducing this picture again. So, the same thing remains here. Now, I am going to look at the price. According to this pricing policy, what is the price paid by yeah. So, tell me, the allocation of this person remains right. This is that. What are the what is the exact description of his price? There was a jump point here and there was a jump point here, right? So, what is this price? Oh, this has gone here. So, if you remember, what is the price? If I read off that formula, because I am trying to prove that that formula and a monotone allocation, any monotone allocation along with this formula, the monotone allocation X, once you fix it, the pricing gets decided. The jump you see, right, that the price has a jump quantity associated. That jump quantity depends on the allocation rule you have decided. But all we know is it's a monotone rule, but whatever that is, that will decide. So, here our allocation rule is this, that if you cross this, you get this much extra stuff. If you cross this breakthrough point, you get so much extra and so on. So, what should be the price? What are we saying is the price value here? My picture is fine, I think, yeah. What? From here to here, nothing changed. This is the base situation. From here, you go here and this one changes. See, the moment I cross this break, this is a flat region. The allocation has not changed. So, that summation has, when we have the jump, beyond here there is no jump. So, this thing contributes 0. So, my base of my rectangle now is this. It is really a area under the curve argument. This is the base. this last jump before your this, right? Okay. That formula I should have realized. I should have put it there. Should I write it there again? This pricing this thing, or else you recall what and write it. Whatever. So this is this VI thing. VI is this. So what is the, now you guys tell me what is the price thing here using the pricing principle. Okay. This thing? Okay, so let's decide the jump points, right? These are the jump points. So, yeah, so now tell me, what is the, how do I compute the price? Use this formula. That is again all, when the bid was here, basically we don't know what the real valuation is, right? The pricing can only depend on the submitted bids. So he is basically saying, so here there are these 3 jump points, correct? So for each of these jump points, this one was this this is up until here it is this, nothing changes. Here it remains this much, basically this rectangle. Here this rectangle becomes this, and this one becomes this. So I should shade this entire this thing. Actually what I did was it VI XIB, yeah, okay. Where is the jump at? Right. Why is this part of this rectangle? I just now realized this portion, should it be part of the rectangle? See, the jump, this quantity, when I wrote this down I realized, see what am I doing is, this is itself a rectangle, the length of this thing, the breakaway point times the jump, right? So this means here I am stacking these rectangles. First jump is this rectangle, the first breakaway point. This is this is where the first jump is. This is this ZJ, and jump at ZJ is this much. Sorry. It should be this much, right? From 0 to this. This should be this area, no?
Ultimately, in the overall shaded.
Yeah, but I made a mistake. That's why I am doing it again. So this, at the first jump, this is the base, this is the height. The second jump here, this is not a jump. Here, what is it? This much is the height. This is the height, and this is the base. So, and the whole thing is the base. This is the base, and this is the height. Therefore, the second is this much, right? This is why, because see this jump this is Z1, this is Z2. Let's write it. Correct? Yeah. This is why this portion. Yeah. I realized when I was shading this. Okay, because sorry. Yeah. So this is why again this is Z1, Z2. Now this guy is crossing Z3. So initially this is this region. Second time this one was the region, and the third time it's actually okay. Second time would have been this region, right? This stacked rectangle. So let's use different shades so that it's clear how the shades came about. Okay. This is a cleaner diagram. This is the Z2, this is the Z3. Okay. Now here, yeah, only one, this, here, that's it, nothing more. Okay. Now, if I subtract this from this, that would be the utility. By the way, I should write here bid plus var. Sorry. So this minus this, so it is Vi xib minus Pi. So what region should I get here?
Small. Between inside that.
This whole thing, because this is this big rectangle and from here, right? So now I have to draw the, okay. Do I have green? Okay. Okay, so let's try. Correct? Okay. This is Pi. This doesn't matter. So yeah. So now which part of the diagram should I picture? This whole red. See, this is the extra stuff I'm paying. Loss in utility. So horrible, right? This is the how do I say that? This portion. I want to say that this is, I did a very stupid thing. I should have colored this by red to say that red minus blue gives you, this is a smaller this thing, right? So, okay. Yeah, sorry. Usually do this properly, but okay. I'll just use the same hatching thing. It's like from the red part I remove this blue. Okay. Here now this blue part, blue remains. That's the price. This and then this is. So from this red part, this blue goes away, this part, so I'm doing subtracting, right? This is Vi, the utility is given by Vi xib minus Pi. This is the Vi xib, that graph, this is that curve rather. From here I am subtracting this blue region. So this portion goes away. Ah, right, you also have that, that red part also remains, correct. How do we, this thing? Yeah, right, but this one, right? Yeah, I'm just checking if the hatching is correct. Yeah, I don't want. Okay, right? This is, yeah, this is this portion where this next jump happens. Okay, and this. Yeah, so now this is red, yeah, so this red part. Yeah, this thing, right? This.
It's really between the yes, yes.
And this is the base, length of Vi. This is the height. So that's why I'm drawing with this. So whenever we have a red piece left over, what does this mean? So yeah, yes. So here this part basically means that utility is positive. Over there also utility is positive, because actually true, I actually got an item even without bidding low, right? The problem here is, here, yeah, how much large the blue part is vis-a-vis the red part, that will really decide what my residual utility is, because blue part is basically payment that I have given to the system, like this is a loss in utility, because I overbid. This is the extra stuff I ended up paying. Like I bid this much even though my true valuation for this object was this. So I unnecessarily crossed this jump point when I didn't need to. So it's like, for me the slot number 2 is good enough, but somehow I bid so high that I have basically managed to bid slot 1, and therefore of course I have to pay more for it. Okay?
From the graph we can see that the first case is maximum.
Yes. Right? This is correct?
Because in second case there is a negative factor.
Yeah, and this,
Third case is
just this part, right? Whatever this, however this thing maps. So, okay. So does this complete the proof? Okay. Now let's just say briefly, if again this was not a piecewise function, but a more like it was a xi was differentiable everywhere and so on and so forth, it would still be an area under the curve, this same subtraction type of thing, right? Your area under the integration captures area under the curve. Here what did we do? Basically added up, stacked up these rectangles and so on. Over there we would be doing an area, integrating area under the curve, and subtraction makes, it's the same idea. The subtraction comes from the fact that this is how the utility is defined. Okay? Yes, of course. Okay. Okay, the picture over here does not look nearly as bad as I thought. Maybe I should write a few more things. This is the price and this is the utility. Just the, why am I writing VI? Okay. Yes. Now, so okay, let's say, okay, we have gone well overboard. So we will let's come back to this. I wanted to conclude by saying what actually should have happened when it comes to the sponsored search. Okay, given this, that this is the uniquely best pricing this thing that ensures that property and so on, can you say something about the, I mean the class is over, but we are just talking and I'll repeat a lot of these things next class, but can you guys who are here, can you tell me how should the sponsored search pricing rule be? This over here I just wrote how greedily it is allocated. Now the question is, how should they extract money? Yes.